Hi, my name is Sunil Patil. I'm gas turbine program manager, and today we're going to talk about the gas turbine technology roadmap from Ansys. And our vision for the solution in the gas turbine space is and has been simulation throughout the gas turbine product life cycle, from early design to the detailed design to manufacturing to operations and the maintenance, repair, and overhaul. And there are several key aspects to this solution. One of the most important being reducing the design cycle time through technologies such as GPU-based computations, AI/ML, and continue to focus on state-of-the-art methods and workflows. We also, through our solution, want to ensure that we support our customer to their initiatives such as more time on things and less downtime via solutions such as hybrid analytics, fusion modeling, reduced order modeling, and we also uh, support our customers to really accelerate their net zero goals through solutions for hydrogen blends, sustainable aviation fuels, and also the goals such as improving the efficiency and durability of the machines. And we have a variety of technologies in the digital engineering field, such as the model-based systems engineering, simulation process and data management, process integration, and design optimization. As far as the gas turbine technology focus areas are concerned, we do focus on various different important components such as fans, but also on the modules such as compressor, combustor, turbines, and also looking at subsystems and overall system, and ensuring that the key technology initiatives, such as increasing efficiency, improving durability, reducing weight, those are addressed while also meeting the new sustainability or the net zero targets. And all of this is done while leveraging the AIML and GPU-based computations as a method to really accelerate the cycle time and hence help our customers to achieve the faster time to market. And as I mentioned earlier, we do provide solutions for the individual components such as fan and things like blade flutter, bird strike, icing, to the multi-stage aero unsteady combustion, modal analysis, rotor dynamic analysis, structural integrity analysis. But one of also the key differentiator from Ansys side is you can also look at the full gas turbine end to end in a single calculations, and we have done that multiple times. Um, that in a single calculation you can go from the inlet to exhaust, and that provides additional insights into the complex phenomena happening within the gas turbines. Now, I'll briefly talk about the key pillars of our innovation strategy, which are also the important pillars for our gas turbine strategy I mentioned earlier. On the far left, you would notice our continuous focus on core physics, numerical methods, and models. We continue to focus on high performance computing. Over the years, we focus on CPU-based computations, but we also continue to focus now uh, coming up with native GPU-based solvers, and also looking at further in the future to leverage technologies like quantum computing and see how it can benefit simulations. AI/ML has been another focus area for us, and really we are leveraging that for software acceleration and overall accelerating the solution time and um, reducing the product design lifecycle time. We also want to ensure that our products can be run equally easily on the cloud platform, just as they can be run easily on the edge or on the local workstation. And as I mentioned earlier, we have Several technologies in the digital field, which are clubbed here in this intelligent engineering pillar, such as the MBSE, the process and data management, simulation process and data management, digital twins, mission engineering, and so on. Now, with that background, let me deep dive into some of the key aspects of our gas turbine solution. And we have a significant focus and I would say a lot of focus, especially on the CFD side for native GPU computations. Now, just to provide a little bit background into that, if you look at this chart at the bottom, uh, you would notice that even the CPU-based computation, we have made enhancements in past more than decade to make the calculations on CPU hardware fast. But we introduced a native GPU solver 2 years ago, and you can see a significant increase in speed up. Uh, such as, a high-end GPU card such as H100 is, about 10 times faster than running on 100 CPU cores. And uh, our overall strategy of leveraging GPUs natively is really providing a faster turnaround time. It is also providing a much lower energy consumptions to get a solution, and it is providing the overall cost savings, including the hardware cost savings. So as I mentioned, we introduced this native GPU solver for CFD in 2022, and you can see we had several releases, and uh, by the latest release, we have now all the fundamental capabilities as well as some of the advanced capabilities which can address a lot of the complex problems for gas turbines, including the gas turbine combustion, some of the turbo machinery aspects, as well as many steady and unsteady phenomena happening inside the gas turbine. And I'm going to cover some of such example in next few slides. I also wanted to mention that uh, our GPU solver really scales well, and it can also leverage different hardware. So in past couple of years, we published a lot of benchmarks on the NVIDIA hardware. This year, 2024, we officially started supporting AMD hardware as well. And here you'll see one of the benchmarks on the 250 million LES case. Um, and you would notice that even on the AMD hardware, we do a really good performance scaling, parallel scaling, um, and um, the key point I wanted to mention here that the native GPU solver provides all those significant benefits, which I mentioned in the previous slide, on all different kinds of hardware. Uh, we have shown on NVIDIA, and here I'm showing on AMD, and we have done several such benchmarks. If there is interest, please let us know. Uh, this is gas turbine specific benchmark. This is a generic aircraft engine combustor. This is a relatively small case, I would say 6 million polyhedral cells, but it has sprays, which is modeled with DPM with 4 million particles. And you would again notice that with GPU, we get significant speed up. And what this really boils down to that if you use, let's say, one 800 GPU card, it can replace 700 CPU cores. And then you can keep on adding more GPU cards, especially if you have a larger number of cells or mesh. and it will provide further speed up into the overall solution time. Also cover a few of the turbo machinery examples here. The first one here is a 1.5 stage compressor, run fully transient, full wheel, and this is a transonic compressor. Here's some of the details, the way we ran this case. And you would notice that the solution from the GPU solver matches with the reference solution from the validated CPU solver. And once we do that, we see a significant performance benefit by running on GPU. And here, we actually use a lower-end GPU card, L40, and even on that card, just one quad L40 node, we are able to get solution for this 1.5 stage full 360 unsteady sliding mesh case with a solution which was just about was taking a half a second for a given time step, uh, which provides, as you can see, significant speed up compared to running on CPUs. This is further extension of that is 2.5 stage compressor. And again, you would notice that the solution from the GPU solver overlays on the CPU solution in terms of the signal, in terms of the frequency spectra. And this is a little bit bigger case, about 100 million hex element, and we can still run on higher number of lower end GPU cards and still get solution in less than a second per time step for this full wheel unsteady sliding mesh case. And this is just to highlight the strength of the fully native implementation to really take advantage of the GPU hardware. This is 3.5 stage high pressure compressor of an aero engine. We ran this full multi-stage, full wheel. This was about 500 million total cell count. And we ran this case with large simulation, and we're able to run the full wheel or full revolution of this full multi-stage compressor in just about 8 hours on 3 GPU nodes. And that provides the strength of native GPU solver to run these high fidelity transient calculations much more faster, making it much more practical, much more applicable in the regular production environment. Now I'll move on to the other important pillar, AI/ML, and with Ansys AI, we are providing a solution to really accelerate the design cycle time. We have 3 different offerings under Ansys AI. Ansys GPT is basically a virtual assistant to Ansys product. It is a natural language, a large language model assistant for documentation and training for your day-to-day usage of our software. Ansys AI Plus is primarily an AI add-on to different Ansys flagship solvers across our portfolio. And Ansys SimAI is a machine learning platform for simulation across the physics. It's extremely fast and reliable, provides reliable physics predictions, which this AI model learns from your existing data and provides solutions to the new geometries in a matter of seconds. So let me explain a little bit more details, SimAI, which, as I mentioned, really meant to provide the solution significantly faster and to really provide a way to substantially accelerate the cycle time. The idea is to use a machine learning platform to use the existing data. So you can upload your passed a newly generated data to this platform, and that data is used to train the AI model. And once this AI model is trained, then you can pass the new design, new geometry to this AI model, and it will start predicting in a matter of seconds. So you can really unleash the power of AI for the gas turbine design with Ansys Sim AI. Um, as I mentioned, it's a cloud-based machine learning platform for simulation where you can train the AI without having to parameterize your geometry. You can predict the performance across the design changes. Uh, you can leverage previously generated data to train the model. Uh, you can always generate the new data and continuously keep on training the model. So it can continue to evolve. Um, and on top of that, ANSYS SimAI is physics neutral. It's applicable to any physics such as fluids or aero, mechanical, electromagnetics, optics, applicable across all different industries such as aerospace and energy, automotive, works with any 3D simulation data, whether it is ANSYS generated data or it is generated by your in-house solver or third-party tools. And here I'm presenting the generative AI case using SimAI for the gas turbine compressor airfoil design. So, and I'm presenting the airfoil design or the blade design because that's one of the areas where a lot of time is spent for within the design phase for the gas turbines. Um, and here what we did was we use the existing aero as well as structural data. So we use about 150 simulations, CFD, and different modal structural simulations to train the SimAI model. And once that SimAI model was trained, we're providing a new designs to the SimAI through a data generation engine, which uh, generated different designs with the use of OptiSlang, and it was able to predict the uh, the performance, predict the results for those new designs in matter of seconds. And you can see for this is a one outcome for the CFD results and the predictions from SimAI, as you can see for the pressure distribution in this case, match very well if you actually run a CFD calculation for this for that new design. Now, the only difference uh, is the running 3D CFD calculations can take some time while the SimAI is giving you the results in just a matter of few seconds. So I talk quite a lot about SimAI, but also the AI Plus, which basically is AI ML technologies embedded in our solver, also provides significant advantage for our gas turbine customers. And I'll cover a couple of examples here, one on the aero side and one on the mechanical side. This one is on the aero side or CFD side. The turbulence model optimizer in Ansys Fluent uh, is part of the AI Plus offering. So the AI technology along with a joint is used basically to calibrate the RAN space Gecko turbulence model coefficient using the training data coming from high fidelity LES simulations. And that really makes that two equation Gecko turbulence model to similar class of problems with increased fidelity because it's leveraging the training from the high fidelity LES calculations. So such Turbulence Model Optimizer is now available as part of the AI Plus offering. On the mechanical side, we we have been leveraging the solution statistics from the millions of solver runs anonymous for the resource prediction, including the solver choice, speed, memory, and the required disk space. Um, and that is a powerful tool for our mechanical users for various class of problems related to the structural analysis for gas turbines. Now I'll cover some specific areas related to turbomachinery or the blade rows. And I wanted to mention here that we continue to focus on CFX for the turbomachinery capabilities. And here you will see in this chart, in past couple of years, there was a lot of enhancements done in CFX, which were driven directly from our gas turbine customers, all the way from the end-to-end workflows to the detailed capabilities related to the film cooling, harmonic balance method. In fact, this year we are introducing a completely new paradigm for harmonic balance method with the time decomposition harmonic balance approach. So significant enhancements have been done in just past couple of years, and we continue to deliver on the turbo capabilities using the customer demand. Uh, Here you will also see some of the pre and post-processing related focus associated with the overall turbomachinery solutions. We introduced the Blade Builder product, which is again provides a very streamlined workflow going from your mean line design or preliminary design to the blade room meshing to the CFD analysis. We also have introduced the hybrid meshing in past few years, past few releases, and continue to build upon it in TurboGrid. This year, we also had first release of PyTurboGrid, which allows a Pythonic framework to be used for uh, automating the meshing as well as further enhancing the overall capabilities, including ability to do the meshing for multiple components simultaneously and also several post-processing related enhancements related to visualizations or just the overall performance improvement to get results faster or get results post-process faster. Um, On the CFX solver side, as I mentioned, this year we also introduced first of a kind time decomposition harmonic balance method, which provides order of magnitude speed up. We also have introduced now mixed fluid solid interfaces to facilitate a better setup of the high pressure turbine blades. We have new dynamic variables to aid the conversions. There are capabilities now to automatically repeat the time step with a reduced time step to again improve the overall robustness for various class of problems or the solutions across a wide range of operating conditions and several new models to improve the accuracies, for flows like bubbly flows and wall boiling applications and so on. I didn't mention about the Blade Builder, which is a new product, and it sits inside Ansys Discovery. It provides a modern 3D CAD environment for turbomachinery. So the idea is you can bring in your bring in the data from your blade design tool and that can be just the data from your mainline design tool. And we then can help you create the 3D CAD from that data and also help you help you further modify that data. For example, if you want to add some complex details like complex fillet or squealer tip or partial tip gap and things like that, you can easily create those features and then pass automatically all that information so that TurboGrid can create hybrid mesh in a much more automated manner. So this Ansys Blade Builder provides a streamlined workflow going from mainline design to CFD, but it also provides this modern 3D CAD geometry environment for turbo machinery. I did mention about Ansys TurboGrid. Many of you might be familiar that it provides an automated way to create a hex mesh for the main gas path. But in the past, 4 to 5 years, we introduced and built upon the hybrid meshing, which can handle the complex details such as the squealer tips, secondary flow paths. And the idea is to still have mostly hex mesh in the main gas path. Only in the region of complexities, you can choose to have unstructured or TET mesh, but then have a proper one-to-one connection to the main gas path hex mesh. And that really provides the benefit of having overall low cell count, but still have a really good quality mesh, which provides much more accurate solution, again, while maintaining that accuracy of mostly hex mesh in the main gas path. And as I mentioned, we really are continuing to expand this hybrid meshing capabilities for various complex details such as casing grooves, complex blade ends, non-axisymmetric end walls, shrouded blade ends, and so on. Uh, we are also continue to provide the solver APIs and ensuring that the broader Pythonic ecosystem or Python ecosystem can be leveraged for various different needs, whether it's just a customization of your workflows or automation or putting in additional capabilities. So we introduced PyFluent in 2022. We released PyTurboGrid, as I mentioned, this year, which provides the automation as well as the ability to do a multi-stage meshing. Um, and we are also working on introducing PyCFX and PyRocky very soon. And here is an example of PyTurboGrid, which can be leveraged to really fully automate the meshing process for the bladed components. But here, as you can see in this example, this is 4.5 stage compressor, and we were able to mesh all these rows simultaneously using this PyTurboGrid script. So we're just able to create the mesh for this full compressor, 4.5 stage compressor in less than 5 minutes using the PyTurboGrid environment. So as I mentioned, it does provide automation, plus it provides an additional capabilities such as meshing multiple rows simultaneously. So I talked significantly our fluids roadmap, or CFD or aero roadmap. Now I'll move on to the mechanical roadmap. And we really have significant focus on overall gas turbine workflows for thermal analysis, such as emission and flight cycle analysis, structural analysis, and dynamic or explicit analysis. So I'll cover some of the key areas and we'll talk about different workflows for those key areas and how these workflows are making this overall analysis faster and streamlined. So I'll start with the whole engine modeling, where the ultimate goal was to determine the global behavior of the engine while predicting things such as structural integrity, for example, clearance or clash check, rotor balancing, etc. And also providing the boundary conditions for subsequent detail analysis. So now we can link these different disciplines such as thermal and structural consistently. We can reduce the computational complexity while building in the best practices for this whole engine modeling while providing specialized elements. And that is really reducing the time needed to solve such finite element analysis. And it also makes it easy to stay within the one known software instance. The flight mission definition through mechanical scripting. So the use of scripting in workbench mechanical or mechanical application to really pull the data from the external sources can be effectively used, as you can see in this demonstration video on the right-hand side, to create contact pairs or to create the mesh settings, analysis settings, apply loads and boundary conditions automatically. So you can really take advantage of the workbench mechanical geometry-based pre-processing while also utilizing complicated load case management from the external data utility. So you can automate a lot of these repeating processes with full scriptable capability of the mechanical tree. We also introduced multi-stage cyclic symmetry a few releases back, which really helps with the engineering goal of significantly reducing the computational time for things like the modal analysis. So uh, you can now do the multi-stage analysis in mechanical for static, modal, and linear perturbation modal analysis. And here you can see previously for such a kind of analysis, one needed to really do a full 360 analysis, but now you can just model a single sector per row, and that really accelerates the design process significantly, typically more than 100 times faster, um, because such analysis is proportional to the power of 2 or 3 of the total number of degrees of freedom. And you are really substantially reducing this number of degrees of freedom, as you can see between these two comparison between full wheel solution with million elements compared to just 40K elements. And you can see dramatic reduction in the solution time going from several hours to less than 3 minutes. We also introduced harmonic balance approach for mechanical this year. And really the advantage here is you can get a significant time savings compared to the full nonlinear transient solution. You can solve for the periodic solutions using the dynamic analysis where you can still account for localized nonlinearities. And such applications involve different gaps or clearances, crack plate, friction dampers, bolted assemblies, hydrodynamic bearing, squeeze film dampers, joint stiffness based um, uh, on the experimental curves, all these different applications where you can make use of the harmonic balance approach. And now at release 2024 R2, harmonic balance method is also applicable to cyclic symmetry, which makes it uh, much more advantageous for turbomachinery problems. The bladed disk response or a force response analysis that has been our focus for many years. And since release 2022 R2, we now provide a ribbon, um, uh, a detailed menu tab inside the mechanical application ribbon where we have automated a lot of the pre and post processing steps needed to carry out the force response analysis of things like uh, getting the data, unsteady pressure data or the engine order data from CFD, mapping that onto the mechanical mesh, ability to get the interference diagram to look at the crossings, and easier way to carry out the mistuning, or easier way to account for aero coupling, and a lot of turbo-specific post-processing, such as looking at the full expansion of the results, such as the displacement, mean stresses and strains, and also getting the data for lifing analysis in the right format. Even we now provide the ability to uh, create a lifing diagram such as Goodman diagram, which gives much better view and all uh, that post-process data can be used effectively for fatigue and lifing calculations. Inverse analysis, especially things like hot to cold workflows, are important in gas turbines because of the very nature of aerogeometry being hot and the mechanical typical starting point being cold. So we now provide within mechanical application, and I will play this video demonstration here, provide a way to obtain the cold geometry by performing the inverse solve, which subtracts basically the effects of loads and boundary conditions. Um, and this combined with some of our capabilities within space climate discovery really allows you to obtain the cold geometry again by performing this inverse analysis. Bottom up substructuring is also another key area, and things such as the substructure generation, including pre-stress. We are now providing export import of multiple formats, including load vectors, ability to create patterns, and an expansion capability for detail analysis, which really helps for assembly optimization, which is again enabled through the faster analysis. And it also can be used to help protect your company IP. Fracture is another key area, and we provide the solution in this space through the our smart solution, which is in a basically powerful, easy way, uh, provides various solution, including powerful, easy way for to use meshing feature for standard complex crack profile. It provides user controls for remeshing advanced cracks. There's extensive support for temperature dependent fatigue crack growth laws, and also initial stress strain fills with crack closure effects. or support for fatigue crack growth in bodies with evolving nonlinear contacts. This smart feature is really evolved over time, has all the fundamental and advanced capabilities which can be leveraged for the fracture analysis for gas turbines. Fluid network modeling, that's the another important area, especially for carrying out the transient thermal analysis, where you want to, let's say, have a simple conjugate heat transfer analysis between the secondary flow paths and the metal surfaces. Um, so Fluid 116 element has been there for a while, but we have now this new capability in workbench mechanical application for sketching the fluid networks and the with the construction lines, and then we can promote these lines on to line bodies and project them onto the right surfaces. So you can really sketch your these networks interactively without going back to the geometry editor. These fluid networks are automatically connected back to the metal surface or edges. They can be done based on name selection, so you can do further automation, and hence eventually you can run the full thermal transient with simple CHD. For gas turbines, especially for jet engines, the phenomena such as the bird strikes or foreign object damage, containment are important, and LSTANA is gold standard for that. And we have been doing more extensive LSTANA exposure in Workbench, and that's really providing linking of needed different models of subparts to carry out larger uh, module level or system level analysis. It reduces the time needed to solve the overall finite element analysis. You can stay within the one known software instance and reduce the extensive hardware test. Similar to CFD, HPC has been the focus area for Ansys Mechanical over the years. And here, we are highlighting the uh, the high performance computing for uh, one of the turbo machinery case with 1 billion degrees of freedom. And that model was solved with the SPAS solver at 2024 R1 release using more than 1,000 cores with 21 CPU or 21 compute nodes. And here you can see over the year uh, the number of cores uh, which we have been testing and where we see a good speed up has continuously increased substantially. And as you can see, even for this case, even after using thousands of core, we do get good parallel scalability. Also, the performance on the mechanical side, one can leverage the GPU computing and through the acceleration. So this is not the native GPU computations which I mentioned about in context of CFD, but still, if you have the GPU available on your hardware, that can be really a leverage to get significant relative speed ups. Um, Currently, we do support the GPU cards from NVIDIA, AMD, and we'll also support the other cards as they become available in the near future, such as the Intel cards. Additive is another focus area for that, and it in itself is broader area to cover, and we continue to develop our overall comprehensive additive solution. But I just wanted to highlight here that we signed an agreement with Materialize last year. So the solver engine from Ansys will be available to those Magic users from this year. And it also provides streamlined link between the Magic and Ansys. But as I mentioned, we have and will continue to further enhance our comprehensive additive simulation capabilities through mechanical. Finally, I'll cover the sustainability topic, and we understand the very very challenging net zero targets for the gas turbine OEMs, and we are developing best practices for alternative fuels such as hydrogen, hydrogen blends, ammonia. That has been a significant focus on our combustion modeling side. We have modifying some of our combustion modeling, introducing new models, making these models available on the GPU, uh, but also more importantly, developing the best practices for modeling these hydrogen blends, ammonia to simulate complex phenomena such as flashback, um, lift up, and so on. And we have also published several papers through the Turbo Expo conference as well as the ASME journals, which also cover these best practices. So if you have interest in learning more about these best practices, please reach out, and we are more than happy to work with you and share some of these additional details other than what we already published in the open literature. I also wanted to mention that we have strong collaborations with several universities on the topic of sustainability, and I'm just highlighting few key collaborations here. So we have strong collaborations with University of Central Florida uh, in the topics related to the sustainable aviation and the energy transition. We have continuous several years engagement with University of Florence on various different topics related to the gas turbine combustion. Also collaborations with DLR Germany on the hydrogen combustion. In North America, we have strong collaboration going on with Georgia Tech, again, with a lot more focus on hydrogen combustion, but also in general in the area of combustion dynamics. And there are also uh, several other universities in the APAC region like KAIST and KAUST, with whom we are collaborating on the topic of sustainability linked to gas turbines. And just very briefly, I'll cover another area, which is hydrogen embrittlement, which is a complex topic, but we are developing solutions to look at various aspects related to hydrogen embrittlement, such as the diffusion of hydrogen, use of crystal plasticity, as you can see in this chart, to consider the diffusion of hydrogen at the grain boundaries, having ability to have material properties as a function of the concentration of hydrogen, the temperature and pressure, and the damage, ability to do the calibration of materials. We're providing all these different technologies to really look at the hydrogen embrittlement as a much broader, comprehensive topic linked to the sustainability. And finally, I will wrap up here. I did talk about different technology pillars of our overall strategy and roadmap for gas turbines, key technologies such as GPU-based computations, AI/ML, core physics, numerical methods for aerodynamical analysis. And uh, that has been focus for us for many years. And we have been leveraging that to provide state-of-the-art solution to our gas turbine OEMs. And as part of that, we have collaborations with all major gas turbine OEMs. And I'm highlighting here some of the collaborations, some of the represented collaborations, and some recent press releases, uh, our collaboration with Pratt& and Whitney in the area of digital transformation and sustainability, our collaborations with Rolls-Royce to really reduce the design cycle time substantially. Also collaborations on the materials side, collaborations with Safran Aircraft Engines, again, to realize the benefits from simulations to uh, to substantially reduce the overall cycle time through the virtual prototyping. And also very recently, you would have noticed these videos and press releases between the collaboration between Ansys and Honeywell, which highlight how Honeywell uses simulation for the aircraft engine design. So with these uh, great stories of our collaboration, I would like to wrap up this talk on the Ansys gas turbine roadmap. If you have any questions uh, or would like to follow up on specific topic, please reach out to us. Thank you.